All right, let's dive into a topic that honestly affects pretty much everything we rely on today: predicting when things are going to fail. We're going to explore what's called the friction in failure prediction, which is really just a way of asking, why is this so incredibly hard to get right? You know that feeling, right? One minute, your phone is working just fine. The next, it's a brick. Your car seems perfect, and then bam, you're on the side of the road. Or think bigger, like a massive factory machine that just suddenly stops, costing a fortune. We've got more data than ever. Our computers are ridiculously smart. So, what gives? Why can't we see these things coming? Well, it turns out that getting that predictive superpower, that crystal ball for machines, is not so simple. When you dig into the research, it really boils down to three huge interconnected problems that keep getting in the way. So let's break them down one by one. First up, we've got what we can call the data dilemma. Think about it like this. Any prediction model, no matter how fancy the AI, is like an engine, and that engine runs on data. But what happens when the fuel itself is contaminated or just plain bad? Well, the whole thing sputters and fails. This data problem really comes in three main flavors. First, there's something called censored data. This just means we often don't see the full story. Say you're testing a part for 1,000 hours. If it doesn't break, your test ends. But maybe it would have broken at hour 1001. You just censored the actual failure point. Then you have noisy data, sensor glitches, temperature swings, stuff that just creates a messy, confusing signal. But the weirdest problem, the one that feels totally backward, is imbalanced data. So here's the paradox. In the real world, fewer failures is a great thing, right? Of course it is. But if you're an AI trying to learn what a failure looks like, it's a disaster. Imagine trying to teach a computer to spot a polar bear, but you only show it one picture of a polar bear and 10,000 pictures of a black cat. The AI is just going to learn that everything is probably a black cat. That's imbalanced data. And this quote just hits the nail on the head. Because failures are so rare, these super smart algorithms actually develop a strong bias. They learn that the safest, most accurate bet is just to predict that everything is fine all the time, which, isn't very helpful. Okay, so let's just pretend for a minute that we've solved the data problem. We've got perfect, clean data. Now we hit the second hurdle, the complexity conundrum. And the big lesson here is that just throwing the biggest, baddest, most complex AI at the problem isn't always the smart move. You're always facing this fundamental trade-off. On one hand, you've got these incredibly complex models, like deep neural networks. They can be amazingly accurate, picking up on tiny patterns nobody else can see. But on the other hand, you've got simpler models. They might not be as sharp, but they're fast, and this is key. You can actually understand how they work. It's a constant tug of war between accuracy and things like speed and trust. And that brings us to the famous black box problem. The most powerful AI models can tell you a failure is about to happen, but they can't tell you why. Now, if you're an engineer about to shut down an entire factory floor based on that prediction, the computer said so is just not going to cut it. That lack of transparency is a huge barrier, especially when the stakes are really high. And then there's just the brute force reality of it all. These complex models have a really high cost of thinking. They need massive amounts of computing power to run. So what good is a model that takes 3 hours to predict a failure that's going to happen in the next 5 minutes? It might be interesting for a research paper, but in the real world, it's totally useless. And that brings us to our third and final friction, the integration impasse. This is the point where a beautiful model, built in a nice, clean lab, walks out into the messy, chaotic real world and falls flat on its face. Because a model that's perfect for one machine can be a total failure on another. You see, real systems are just messy. They create all sorts of different data, vibration signals, maintenance reports, photos, you name it. And just getting all that to work together is tough. But the even bigger issue is what's called generalization. A model gets really, really good at understanding the specific quirks of one machine, but then it can't adapt when it sees a new one or even when the old machine just starts operating a little differently. This little 3-step story is the perfect example of the generalization trap. Step 1, you build this absolutely perfect AI model on all the data from machine A. It's flawless. Step 2, you take that same model and deploy it on machine B. Maybe it's the exact same type of machine, just in a different room. And step 3, it fails miserably because machine B has its own unique personality, its own operating conditions, and the model just can't handle it.
So, we've looked at these three massive frictions: the data problem, the complexity problem, and the integration problem. Where does all of this leave us? Let's put all the pieces together for the big picture.
This right here sums it all up. You've got the data dilemma, where the very foundation of your prediction is shaky. You've got the complexity conundrum, where you're constantly trading off accuracy for things like trust and speed. And finally, you have the integration impasse, that huge gap between the lab and the real world. The key takeaway is that you can't just fix one of these. They're all tangled together.
And that really leaves us with one final, pretty big question. Everything around us is just getting more complex, more connected, spitting out more data every second. So, given these really deep, fundamental challenges we've just talked about, is our ability to predict failure ever going to catch up? Or are we destined to always be just one step behind? Definitely something to think about. Thanks for joining me for this explainer.